Hi, we're going to be understanding GABA and Vigabatrin, don't know how to pronounce it, mechanisms of inhibition and seizure prevention. Um, all right, gamma aminobutyric acid, GABA, serves as a pivotal neurotransmitter within our central nervous system. Its significance lies in its dual functionality. Firstly, GABA predominantly acts as an inhibitory neurotransmitter, effectively tempering neuronal excitability. When GABA binds to receptors on a postsynaptic neuron, it initiates a cascade of events that culminate in the suppression of neural signaling. Secondly, GABA interacts with two principal receptor types, GABA-A and GABA-B. These receptors act as gatekeepers on the neuron surface. When GABA binds to them, it prompts hyperpolarization within the neuron, impeding its ability to generate an action potential and thus exerting inhibitory control over neuronal activity. In essence, GABA plays a pivotal role in regulating neuronal excitability through its interaction with specific receptors, ensuring the delicate balance of neural function within the central nervous system. All right. GABA exerts its inhibitory effects by binding to specific receptors on the postsynaptic neuron known as GABA receptors. These receptors come in two main types, GABA and GABB. Which I just said, when GABA binds to GABA receptors, it triggers the opening of chloride channels, allowing chloride ions to enter the neuron. This inflection negative ions leads to hyperpolarization of the neuron, making it less likely to fire an action potential. On the other hand, GABA binding to GABA-B receptors initiates signaling pathways that modulate neuronal activity through different mechanisms. Overall, the activation of GABA receptors play a pivotal role in regulating neuronal excitability and maintaining the delicate balance of neurotransmission within the central nervous system. Understanding the mechanism of action of GABA elucidates its role as a potent inhibitory neurotransmitter. Upon binding to GABA receptors, GABA facilitates the opening of chloride channels, allowing chloride ions to enter the neuron. This influx, like we just said, of negative ions hyperpolarizes the neuron, raising the threshold for action potential initiation. Consequently, the neuron becomes less excitable, leading to inhibition of neuronal firing. Meanwhile, the binding of GABA to GABB receptors initiates signaling cascades that modulate neuronal activity through various pathways, contributing to the overall inhibitory effect of GABA within the central nervous system. In essence, the intricate interplay between GABA and its receptors orchestrates a finely tuned balance of neuronal activity, crucial for maintaining proper brain function and homeostasis. All right, Vigabatrin. Its mechanism of action hinges on its ability to irreversibly inhibit the enzyme GABA transaminase, however you pronounce it, a crucial player in the breakdown of the neurotransmitter GABA. Structurally, Vigabatrin features a vinyl group that reacts with a key amino acid residue within the enzyme's active site, forming a covalent bond. The covalent modification effectively disables GABA transaminase, preventing it from metabolizing GABA into succinic semialdehyde. Consequently, there's an accumulation of GABA in the synaptic cleft, bolstering inhibitory neurotransmission. This enzymatic inhibition mechanism underpins Vigabatrin's efficacy in preventing seizures, making it a valuable asset in the management of epilepsy and other neurological disorders characterized by excessive neuronal excitability. Vigabatrin, an anti-epileptic drug, plays a vital role in preventing seizures by modulating GABA levels in the brain. It achieves this by inhibiting the enzyme GABA transaminase, which normally breaks down GABA. By inhibiting GABA transaminase, Vigabatrin effectively increases GABA levels in the brain, enhancing its inhibitory activity. This augmentation of GABA ergic inhibition helps to dampen excessive neuronal excitability, thereby preventing the propagation of abnormal electrical activity associated with seizures. In essence, Vigabatrin serves as a valuable tool in epilepsy management by bolstering the inhibitory actions of GABA, thereby mitigating the occurrence of seizures and improving the quality of life for individuals affected by epilepsy. Oh no. Okay, so understanding how Vigabatrin prevents seizures involves delving into its mechanism of action within the brain. Seizures arise from an abnormal synchronized neural firing. By increasing GABA levels, Vigabatrin enhances inhibitory neurotransmission, effectively dampening neuronal excitability. This inhibitory effect helps to disrupt the spread of abnormal electrical activity, preventing the initiation and propagation of seizures. Furthermore, by bolstering GABA ergic inhibition, Vigabatrin contributes to maintaining the delicate balance of neuronal activity, reducing the likelihood of seizure occurrence. Thus, Vigabatrin's mechanism action exemplifies the importance of GABA ergic modulation in seizure management and underscores its significance in improving the lives of individuals living with epilepsy. In summary, GABA acts as a pivotal inhibitory neurotransmitter in the central nervous system, regulating neuronal excitability through its interaction with specific receptors. Vigabatrin, an anti-epileptic drug, prevents seizures by enhancing GABA ergic inhibition by inhibiting GABA transaminase and increasing GABA levels. Vigabatrin effectively reduces neuronal excitability, thereby thwarting the initiation and propagation of seizures. This mechanistic understanding underscores the critical role of GABA ergic modulation in seizure management and highlights the therapeutic potential of drugs like Vigabatrin in improving the quality of life for individuals affected by epilepsy. Understanding these mechanisms provides valuable insights into the treatment of epilepsy and other neurological disorders characterized by aberrant neuronal excitability.